All right, welcome everybody. Hopefully these microphones are all working. So today I'm going to talk to you about the title is Efficient, Scalable, Vision-Based Onboard Autonomy Under Uncertainties, and it's probably all about burning all the cycles that Rodolphe was worried about. So in all the things that he saved, I probably killed a bunch of trees building these slides. So anyway, there's a bunch of buzzwords here. What I'm going to do is try to walk you through what we've been doing. It's sort of a 5 to 10 year vision. We're not there yet, but I'll give you a sense of sort of what we've accomplished and where we're headed. Talking about the work of several students here, Andrea, Koda, Annika, and the postdoc Yulin. You'll see their names show up quite a bit as we go along. Anyway, thank you for the invitation to give the presentation today and give you a sense of the kind of work that we've been doing at MIT in the Aerospace Controls Lab. So my lab, as mentioned, we focus a lot on multi-vehicle stuff. I used to work in space robotics. I've worked on UAVs. I've worked on ground robots. I'm somewhat vehicle agnostic, although I'm in an aerospace department. My home is sort of aeronautics and astronautics. On the other hand, you give me something cool, I'll work on it. I'm open to it. So as you see, we do work. I've actually done work underground. I do work on the surface. I do work on manufacturing, where in those cases, a lot of the uncertainty deals with propagation of not just the other vehicles in the world, but also the people in the world. And so dealing with that type of uncertainty, same type of thing. We've been working with Ford and several other companies on autonomous cars. And if you've done work in that field, you know the actual driving of the cars, the easy part is dealing with everything else in the world. It's the complicated part. We've done the search and rescue and things like that in the forest, which is sort of interesting because then it got me really into thinking about the localization. And if you work in the field of robotics, you can tend to have your little niche and you work on that piece. But when you go to implement these things, you realize just how important the entire autonomy stack is, and that if you just work on your piece and inherit bits from other researchers, perfectly legitimate way to proceed, but what you tend to recognize and bump up against are the limitations of the other tools that exist. And so as a result of that, although my background is in control systems, I came to this field from the planning side of things, and I worked much more on the vision side of the autonomy stack than I ever did before, the primary reason being to begin to recognize just how hard it is to get the information into the vehicle. When we teach control systems, we often think about common filtering, and we have sensors, you know, with sort of white noise stuck onto it. That's a very, very idealized model. And I'm not talking about the white noise part. I'm simply talking about that's what the measurement structure looks like. The world, when we deploy it, is much different than that. And like I say, that's a result why I've been spending a lot of time thinking on the perception side of the stack and not just the planning side. So what you'll see I'm going to give a talk where we'll talk about the planning side, but you'll also see how we then move into the perception side as well. So I'm motivated by this type of work. I'm not actually going to talk about these kinds of examples. I'm going to sort of extract this a little bit and think a little more in terms of the different pieces of the autonomy stack we've been working on. Our sort of the list of challenges are numerous. These are the ones I've sort of going to focus on over this talk. But when you work on multi-agent systems, as I mentioned, the perception, the limited capabilities of the field of view sensors, you know, you stick a camera on there, you think it's going to be great. Well, it's not. It's looking at a certain part of the world. Figuring out what the hell it's looking at in the first place is hard. And then furthermore, you're only looking at that part of the world. You want to know something else, you've got to actually make a decision to look there. And so that's a part of the planning problem, right, of thinking about where to look. And then extracting the information from what you're looking at is also quite difficult. So there's that issue. Of course, there's just tons of uncertainty, not just in what you're doing as an agent, but what the rest of the world is doing, what they're intending to do, what they're actually doing, how well I even know any of this stuff. All of that leads to a lot of uncertainty. The one thing you learn when you go to multi-agent is just how important communication networks are. And I'm not a communication person, so if this sounds naive, it just comes from a lot of experience. But when you deploy a multi-agent system, almost always the first thing that breaks is the communication system. Whatever assumptions you made will be violated almost immediately after you turn the thing on, okay? And so it's just, if you want to make an impact on this field, start here, because it's not going to work as well as you thought, okay? And then ultimately, yes, we are doing a lot of stuff with neural nets, and you'll see me developing that as we go through the presentation. It's really the focus of the talk today. And of course, we're aerospace. You would think about, as soon as you mention neural nets, deep learning, aerospace, people put up their hand and ask the question about what about certification, assurances. And so I'll have some slides at the end. If you want to see them, we'll talk about it. But the two-line summary or one-line summary is we can deploy big things. We cannot certify big things, okay, on the neural net side of it. And the reality is we just can't certify the things that we can deploy. All right? And so that's the short version. I can back that up with some words, but that's basically what happens. So there's a ton of work needed here as well. So I mapped this into sort of a three-space, perception, planning, and scale. It's obviously not sort of a three-space, I mean, in the sense that these aren't really orthogonal, but I'll give you a sense of the different kinds of things I'm going to talk about. So in the planning sort of perception plane, the work I'm doing, you'll hear me talk a lot today about robust tube MPC and imitation learning, really a way of trying to speed up the whole onboard optimization aspect of things. And a very interesting demonstration of that is through the SoftFly collaboration on campus. Perception-aware planning is what Panther stands for, and so we're now migrating into this question of if you're going to plan to do something, that's great, but it's in a world where you don't know very much, so you have to think about where you're going to be looking, and so this now becomes a very complicated problem with collision avoidance. Is not just how to avoid other obstacles in the world, but how to figure out where they're actually going so you can avoid them, and that requires you look and actually decide where to look. Now, many of you work on quadros and things like that. You actually have a degree of freedom, which is yaw, which enables you to point the camera and actually decide where to look, but you've got to do that in a way where you're actually making that choice. Normally you fly looking where you're going. That's not always the best answer. When you get up into here, now we're getting more into the vision. NERF, if you've worked in this field, you know NERF was the sort of idea of the moment last year. Everybody was doing NERF this, NERF that. It has to do with neural radiance field representations of vision systems. You'll see how it comes into play. If you've not seen that, then I'll say briefly what it is. To give you a sense of scale, every one of these dots here is at least 2 conference papers and a journal paper. Okay, so this is that's sort of a fairly substantial amount of work. Similarly, on this axis, I'll talk about the kinds of things we're doing as we try to scale up the perception work and actually think about doing perception at scale, where it's no longer just a single vehicle trying to figure out what's going on. It's now a team of vehicles trying to figure out what's going on. The challenges there are typically you're now dealing with interactions on the scale of images and large-scale data and things that are just not transferable. Going back to the whole communication issue, I can't just take my video stream and hand it to you. That requires a huge bandwidth of capability, and then furthermore, what are you going to do with this thing? You've got your own video stream running and trying to figure out what's going on. The last thing you want is for some idiot to come along and give you another terabit of data and say, here you go, figure this out, because that basically can lead to a situation where everybody now is just over sort of constrained by the amount of data or that they have to actually work with. So this is sort of an axis that we're thinking about here. Then on the planning sort of scale side, I'll talk about the variations which are MATER and R-MATER. MA of MATER is the multi-agent. I'm not sure what the rest of it stands for, but the R-MATER is robust versions of that. Again, trying to address some of the communication issues. So again, you know, how many dots are there here? 6, 8. So we're trying to cover 8 journal papers worth of stuff in 45 minutes. We'll see how it goes. And so if it doesn't seem very deep, that's somewhat intentional. I'll give you a sense of the topics, any interest or any in the deeper knowledge. There'll be the paper references here. Just email me. I'll get you in touch with the students. It's the ones I mentioned before, Coda, Andrea, and Annika. Okay? So let's get started. So, well, okay, before we do that, the goal then is this 3-dimensional middle piece with PUMA. PUMA is the perception-aware, uncertainty-aware multi-agent. And so the perception-aware is thinking about this question where to look. Uncertainty-aware is recognizing that no looking you do is ever going to be perfect anyway, and you're doing multi-agent at the same time. Multi-agent means collision avoidance, mission, sort of combined mission capability. And this is sort of that 3 space, and Coda loves it when I describe this as this is our ultimate goal because that's his thesis, and so he knows that when he gets that done, and I'm happy with it, he can graduate. But we're sort of on the way there, and the point of demonstrating, talking about these other pieces is that they come into play in what PUMA is, and I'll touch on that at the end. There's an ICRA paper that'll be coming up this, where is it, May? That's the beginning that, you know, we have something called PUMA. It's sort of PUMA light at this point, is the way I would describe it. It's not quite a full implementation of the ideas. Okay? All right, so the research directions and what I'm going to talk about out of all that and mention the different dots as we go along is thinking about how to do a sort of efficient vision-based planning. And again, I'll explain this figure as we go along, but basically we're trying to fly a vehicle in a world using onboard optimization as the framework, using vision as the navigation tool for localization of the vehicle itself, plus for some of the perception-aware work that it's doing. Then we expand that to multi-vehicles and explain these pictures as we go along. And then at the end, we're just trying to think about how to build this all into a capability for the vehicle to do collision avoidance and make sure they don't hit each other. And the things that look like flying lampshades are just some of the obstacles that are in the world. There are also quad rotors flying around, and we're trying to avoid them and figure out what they're doing as we go. Okay? And you'll see some videos of that as we go. All right. So in this sort of plane then, we're thinking about planning, so we're actually trying to do something, and at the beginning I talked about the robust tube MPC. It's actually work that was just accepted into REL yesterday, thinking about, well, actually tube nerf was, I guess. But the sort of the sequence of things that are in this plane here are thinking about how to get a vehicle to fly and operate. So what we're looking at is MPC. So I'm not going to go into a lot of detail about what MPC is. Hopefully you're all aware of the words, but basically running onboard optimization. Why MPC versus anything else? It's constraint knowledgeable. It understands the constraints of the system, which have to do with things like obstacles, vehicle capability. It's based on a model, which means you can embed into it the best dynamics that you have. But the net result is that you're basically trying to do planning on a scale where you understand what that vehicle can do. You're trying to avoid obstacles and achieve an objective. But if you've implemented these things, you know that anytime you're doing onboard optimization, one, it tends to be somewhat stochastic in terms of completion time. You don't exactly know where it's going to end. And furthermore, onboard optimizations just don't tend to be fast. And the one experience, the other experience is that it's very easy to pose problems that we can't solve fast enough to implement. Right? And the net result of not being able to solve it fast enough is you're either implementing something that's old or you're not reacting to new information as it comes in fast enough. Right? And by fast, I mean in the sort of typical online optimization with CPUs and GPUs that we currently have, I'm thinking about tens or hundreds of milliseconds, which may seem quick, but isn't fast enough given everything else that has to happen with these computers. Okay? So the question that we had asked was, is there a way to sort of take these optimization results and try to learn them / tabulate them and then extract from that something we can implement which would be much faster, okay? So that's the ultimate goal of what we're trying to accomplish. The approach we're going to be taking, and I mentioned a little bit before, it's called imitation learning. Not a new idea. Imitation learning has been around for a while. Basically what it means is you have an expert and then you just train a student from it, and what you implement is the student. The expert then in this case is going to be the MPC, which is just this thing that's figuring out how to solve these problems, okay? And then you're going to train a student from it. The issue is not so much how does one actually implement that as an algorithm, but how does one do it efficiently so it doesn't take forever to figure out all these expert runs and then basically then train the student from that. You'd like this thing to be faster in learning as well as faster in implementation. So there were two issues we had to address here to think about how to do it, okay? So it's sort of a DAGGR is the standard way of thinking about it, and DA stands for, I think it's domain augmentation, but basically it's data augmentation. But it was sort of one promising approach, but it was the beginning, and we had to figure out how to address these lack of efficiencies that I just described. Okay. So the big picture then is what I'm going to do is fly a vehicle around. It's going to have to solve lots of different kinds of optimization problems. This is the one I described before. I'm flying, this is me flying here. I'm flying around back and forth in this world. The lampshade things are flying around. I got to figure out where they're going. So that's the perception where part of the planning. So I got to look at them. I got to plan that as part of my maneuver, and also then have to do an obstacle avoidance. And of course, the complexity here is you're coupling together things like the position and local and attitude with the actual sort of collision avoidance part of the problem. And again, anytime you start coupling the nonlinear dynamics of attitude with the position solution, you now start getting a very complicated optimization problem. Okay? So we're going to try to replace all this, the standard way that you would implement this, with an MPC running with basically just a learned version of the neural net. And the idea is to get some efficient imitation learning running, ideally be able to certify it. But the net result is we'll take that expert that's doing some type of perception-aware planning, run the thing as a robust version of the MPC, and I'll talk about that in a second, implement this in a form that we can now be efficiently learn what's going to do. This would run really, really quickly, and then we'll be able to certify what's going on. So this is the view from 30,000 feet. We haven't done all this yet, but this is the goal of what we're trying to accomplish, okay? All right, so let's talk a little bit about in detail about what's going on in the planning layer. So again, what I'm trying to do is to fly this vehicle around, and I'm going to learn a neural net that's actually the planner. There's no like optimization running anymore. All the stuff's going to be done offline. I'm going to figure out how to design this neural net, and what I implement is a neural net, and that's it, okay? And there'll be a low-level attitude control running. That's just a simple sort of nonlinear PID. But basically everything else that's going to be running on board that thing is going to eventually end up being a neural net. And depending on the version, the early work I'm going to show you will be actually based on Vicom perception. So we'll take that, feed it in, and say, given this information about where you are, figure out the solution, and then later on I'll replace that with some onboard vision-based systems, okay? Now the typical way that a MPC works is you'd be designing this red line. You just design one path. You just say, this is the path they're going to optimize, and based on everything else I think that's going on, and everything else that's moving around, this is the path optimized. If you go back and look at the robust versions of MPC, there was something called robust tube MPC, and it does exactly what you might think, which is instead of designing a path, the red line, you actually design a tube. The idea being that if a disturbance were to act on you, it's not going to move you outside the tube, and so I can then design a controller at a low level which can keep me inside the tube, and that's great because I know how to get the tube around the other things in the world, okay? So the idea is there might be other things flying around the world, but I've designed this tube in such a way that they're not going to get any closer to me than the width of that tube, and that furthermore I have a controller that will keep me in the tube, and now we have collision avoidance capability based on that type of framework, right? And so robust tube MPC has been around for a long, long time. It's not sort of a new idea. The question for us was, could we actually replicate this kind of robustness through the learned behavior that we're actually trying to do for the imitation learning, okay? So that was the question we had asked, and basically what we were trying to figure out then was, that's on. So just take up, hold a second. Okay, and now I left my glasses up, and now we're back, okay? Okay, so without me touching anything, miraculously this worked. Okay, let's see if this works then. Yes, okay. So the challenge then is, can the imitation learning preserve the robustness of the robust tube MPC? That was the sort of the question we had. That's how it started. So again, what we're trying to do is to basically learn the equivalent of two things that are actually being created. One is what's going on at a low level, and two, how do you actually create this tube and do this robust sort of avoidance maneuvers, okay? So that was how we started off, but then we still are facing the efficiency question, which is how many demonstrations of this do we need to have from my expert? And keep in mind, these are complicated optimization problems, so it's not like we don't want to be running a million of these demonstrations if we can avoid doing so, okay? And so the question was, how do we actually avoid creating all of those demonstrations from the expert that we had? So it turned out that something interesting happened along the way was we realized that what's actually happening here is that the expert knows two things. One, which is how to design the tube, and two, if you were to deviate away from this red line and say end up with this green dot here, what the expert also knows is how to keep you inside that tube, and actually it has a low-level controller that would tell you with that deviation you can now actually implement something else, which is essentially this green line, which would then keep you sort of inside this tube and then essentially try to get you back to the red line and follow it from there. Why is that important? What that means is that through one demonstration, the expert creates one solution of the problem. From that, we can then create lots and lots of data points. Every one of these green dots, which is a perturbation away from the red line, and then look and see how the expert responded, corresponds to another data point that we can actually use to create a demonstration. And the input-output data is what's going to go into the learning procedure. So we got one demonstration, and we can actually get thousands of data points that actually go into the algorithm itself, okay? Which means we only have to run the optimization once to get thousands of data points, and then we can actually hand this to the learning system and say, learn from all this. And you can actually have fairly wide tubes with lots and lots of demonstration, or lots and lots of data points that come from it, and as a result, you can actually have a very efficient way of creating these sort of extra data points that show up. So the extra states and data actions show up as part of this data augmentation process, and again, it just ends up looking like an input-output stream, and that's all we need for the actual learning to happen. So I make the distinction between the number of demonstrations we need, which actually require solving an optimization, and the data, which we basically get for free, okay? Because we can just run the simulation effectively at a different value, and we know exactly what the answer would be. As a result, it's very simple to get extra data points, okay? So two things have been accomplished. Well, we haven't yet demonstrated that we can learn the robustness from this, like the experts are robust. Are we learning enough robustness and retaining it? I'll show you that in a second. But what I am saying is that along the way, what we've discovered is a way to actually very efficiently create the set of data we need to learn from, which answers the first question, how do we get around the bugaboo of imitation learning, where if you go say, I'm doing imitation learning, everybody, the first question they ask you is, how do you get around the number of data points you need? And this essentially does that, okay? All right, so how does it work? Well, this is jumping ahead a little bit, like yesterday, and basically saying, okay, so if you sort of went through everything that we did and get to where we are now, just give you a sense of how well this is working on the computational side of things. These are the kinds of things you would typically see for if you were implementing robust tube MPC on board. This is in milliseconds, right? That's milliseconds, that's tens of milliseconds. So that's pretty quick, and this is pretty normal. And people say, look, you can run those kinds of controllers at that kind of speed. Why would you be doing any kind of learning? Well, the learning is down here, okay? So now you're in tens of microseconds. So you're basically implementing this onboard, very complicated controller right? Or the equivalent of an onboard optimization in what effectively is 0 amount of time, okay? Like most controllers we're going to implement are basically running at a microsecond time scale. So if this is taking tens of microseconds, basically now you can imagine start running this on a microcontroller, right? I mean, the ones that I use for my labs and my classes can only do an input-output sequence in about 30 or 40 microseconds anyway. So to put a 10-second or 10 microsecond step in there, this is all, by the way, just read this neural net, is basically no computation time whatsoever. So this is minuscule amounts of computation. And why do you need that? Well, the one thing you learn when you implement this stuff is computers that you put on board vehicles are never big enough, and I can guarantee that's always the case, because no system I've ever built has ever had too much computation, okay? Why? Because every other system in the autonomy stack typically will just suck up as much computation as necessary, and that's usually the perception stack, part of the stack. It just absorbs whatever is available. So anything you can do here to cut this down, the better off you're going to be, okay? The other thing that's kind of cool is if you think about training time, again, these numbers may not seem huge, but 120 seconds is a couple of minutes, and as you increase the length of the thing, basically we're cutting that down by about a factor of 6 to getting to about 20, 25 seconds. Why is that important? Again, if you want to be doing some type of adaptation and relearning, you'd like to get this number to be as small as possible. So it's not minuscule amounts, but that's a pretty significant reduction. It's the difference between being able to do something in a real experiment versus not, basically, okay? So this gives you a sense of the end result. Let's talk a little bit about what the answer actually looks like. So what's happened, again, we're doing tubes. We're sampling from within the tubes. We get one demonstration. Now, sometimes these demonstrations can be done on software, right? So you just go into a simulation, and you say, here, fly this path around, and the NPC is running while we're doing that. And while it's doing that, we collect that piece of data, that demonstration, sorry, okay? From that demonstration, we can then create all these different pieces of data by doing the sampling with those green dots. And then we take all that data, hand it to a learning algorithm and say, here, learn this, create a policy, and then we take that policy and go implement it. We could implement it in simulation, right? Or we could then go implement it in the lab. And what's cool here is we're addressing the issue of sim to real, right? Which is, if you learn something in simulation, can you actually fly it? Which is like almost never, right? If you've tried this, it's actually really hard. The models, remember, this is model-based NPC. Are your models that you have good enough to actually replicate the behavior of the vehicle? Typically not. So this is why you need robustness in the first place. So that's one of the things the robustness is giving us, is that ability to handle the sim to real. And basically that's the kind of thing that's happening here. Now, what I'm going to show you is actually kind of cool. We can actually go into the lab and fly by hand like a trajectory or ask it to do something. We run the NPC once, we get one flight demonstration, take that one demonstration, go learn a bunch of stuff using the data, and then go back and fly it. Or we can do this from sim to real, right? We actually learn in simulation and then implement in real life, okay? Both very complicated, and again, to give you a sense, this is the number of demonstrations, and I'm, again, making the distinction between demonstrations and data. Demonstrations is sort of how many times you have to run the NPC. Data is what you extract from it. These don't have necessarily a way of extracting those extra pieces of data, so they take more demonstrations. We, on the other hand, are basically here. Basically, one demonstration, we're flying, and so we can go from one demonstration of doing something and then fly in the lab. This is the flown neural net implemented and running. Again, we're using Vicon as the sensing tool here, but basically we're able to fly this around, which again is like I said, that's a remarkable step. You have to think about the fact that you're taking a demonstration in simulation, learning something, and then flying it. And if you think that's easy, go try it, and then you'll understand how hard that is. All of those steps are hard, okay? So this is essentially the first ever demonstration of the data efficiency, right, in the sense of being able to extract the data and be demonstration efficient. And again, to give you a sense of scale, not all these numbers are recent, but we're running at about 180 times faster than what we would have gotten with a robust tube MPC, and it's gotten faster and faster over the past couple of weeks. And part of that has been rebuttal. Reviewers can be annoying at times, but they ask very good questions. And so we actually sped things up and implemented C++ right on the TX2. And again, keep in mind, we're not just flying around in here. We actually have leaf blowers, if you know what these things are, little handheld jets of about 7 meters per second of wind. There's 3 of them sitting here. So while the thing's flying around, there's a howling gale blowing at this thing, and it's still handling that as well as a demonstration of its ability to both tolerate and actually fly, but also handle the types of disturbances that we're putting into the system, okay? So again, the whole point was to try to handle, or actually get to this demonstration efficiency that we talked about, and at the same time be super robust in terms of what we can implement and handle the types of disturbances that we have here, as well as the differences between the model in the simulation and the model in real life. Okay. By the way, I realize I can't see a clock, so this is probably a mistake. So if someone could make a clock visible to me, it would help. Thanks. All right. Now that's all linear, and the first thing you say, well, hold on a sec, this system's not linear, there's nonlinear MPC, why aren't you doing that? So it turns out, not surprisingly, there's a nonlinear version of the robust tube MPC, and if you want to do anything that looks acrobatic, which of course you do, and what I just showed you wasn't, then basically you'd have to go off to the nonlinear MPC. It turns out that nonlinear MPC is an annoying thing, that the low-level controller you need to stay inside the tube is another nonlinear MPC you have to solve, which is super annoying, and nowhere near implementable in real time, or it's very difficult to say at least. So this is where a bit of, I wouldn't say a hand wave, but an approximation has to happen. So we have a sensitivity-based linear approximation of what that controller is that's running at the low level. If we do that, then at least we can have an ancillary control of the low-level thing, which is now efficient enough that we can implement it. It still takes more time than what we had before, but it's basically less than it used to exist. So this is us here. We're these three colors. These are other techniques, and this is everything else. They just sort of fail miserably. There are some that actually do reasonably well in terms of success, but none of them get to the types of training time that we're talking about. And again, these are longer because of the types of things we're doing, but this allows us to do some pretty cool stuff, and I'll show you what it allows us to do in a second. But by acrobatic, I mean that your velocity vector and your z-axis of the body frame are no longer collinear. You're basically now flipping around, you're doing very fast accelerations. And so you have to imagine that even though this is a fairly simple vehicle, you're now pushing this well into an aerodynamic regime that's actually where the actual changes in the flow are going to matter, and yet all of that is captured in this type of design approach as the robustness. We're not modeling aerodynamics, we're capturing it through the robustness terms that we're including, okay? So we can do this for linear, we can do it for nonlinear, and like I say, these are sort of the other baselines, and we are still beating those. What that allows us to do, again, we're running here on a Jetson TX2, which is not very fast. The GPU, as you know, that's probably approaching 8 years old, has the advantage of being very small footprint, relatively small. But even so, we're running these things at about 500 hertz most recently. And what I can show you then is a flip. And this was done sort of 5 times in a row, where again, the only thing running on here is the low-level attitude controller and the learn MPC. So this is learn to flip. And it learned to flip in simulation, and then we implement. We can't do this by hand, right? Well, there's no expert that can go into the lab and do this. So you learn to do this in simulation and then implement it on a real vehicle. And it did it 5 times in a row. It would just go up and down. On the 5th time, the battery was getting very low, so it actually like undershot and then hit the net that's underneath it, and then it just bounced back up again, and everything was fine. It couldn't quite decelerate fast enough, which was the net result. Okay. So as I said, 100% success rate on the first demonstration. Okay, which are again important things to keep in mind. This is sim to real gap, right? And yet able to work the first time out of the box, which is again, not unusual, okay? As is often the case with advisors, as soon as you see something working, you come up with another idea. We say, hey, I have this friend, he has this thing called the soft fly, why don't you go see if you can flip it? And so we took the exact same procedure on this is a vehicle about the size of my finger that has 4 flapping devices on the end that make it look like a quadrotor, and yet everything is different other than the fact that it's a quadrotor. And it has very different flying dynamics, very fast capability for maneuvering, and the result is that we can now actually, I'm not sure how to replay that, but basically, let's just go back to here. That result is, we again, almost on the first demonstrations, we're doing better than the state of the art, and then this is sort of just a new capability that we could implement. Again, the tether here is for power and safety, and we end up at the end of it, and again, that's just sort of a lack of understanding of the full aerodynamics of what it's like to be flying downwards. So things have gotten better. This is sort of a preliminary result. Things are better now, but not quite ready for public release. So I'm not going to show those today, but basically we're very close in being able to implement this. Note that this is 1/10 speed. This is flying very, very fast because it's so small, okay? All right, so that's everything on the the sort of the planning side, not everything, but a lot of things on the planning side. But as you begin to think about moving up into the sort of the other plane, the other parts of that plane, you start thinking about bringing more perception into the loop. The other thing you have to address is the fact that everything I described so far is using Vicon, which is the motion capture, and that tells us where the vehicle is. That's not normally how these things fly around. Normally they're flying around by onboard sensing capability. So what you'd like to do is to take a vehicle, is looking at things on the ground that look like hieroglyphics, but it's basically, it turns out that the tape that we use is very strong and it just pulls the paint up. So whenever we mark things down on the ground, we end up with these sort of markings that look hieroglyphic-like. The net result is these are great features for tracking, and the thing just flies around looking at the ground. It uses those features and figure out where it is, okay? So what we'd like to do is to take everything I just described, right, which is a augmentation strategy for getting extra data points, and include the capability that we're now using vision with a known measurement sort of observation process as part of this. But it introduces a very major challenge, which is as soon as you start thinking about moving those green dots around, like we did before, every time you move the green dot, what you have to be able to do is to essentially hallucinate what is it the vehicle would have seen in this world at the new location. Because if you don't do that, like it's not good enough to just move the vehicle over here and move it to a green dot and say, what's the planner do? That's only half the story. The other half of the story is what would the sensor have seen while you were in these different locations? And I need to have an understanding of what that sensing structure is doing and the observation model is doing. Otherwise, I can't do the extra sampling. If I can't do the extra sampling, I'm back in the problem of if imitation learning is very inefficient, okay? So the net result is you have everything I described before, but now you have an observation model, and you have to account for the uncertainty associated with it, and also what that observation process is like, and how to sample through it. And the net result is we have figured out how to do it, and that's in this tube nerf technique, and I'll tell you what the nerf is used for in a second. But the net result is just like we had the perturbations with those green dots, and then we're looking to see what the planner does. That's sort of this piece down here. What we also have is a sensing model. We understand how the camera works, and as a result, we can also replicate how these other sensing, what the extra sensors or measurements would have been, and then actually get what effectively becomes the policy input. And so we can replicate the equivalent now of the input-output stream that we would have gotten had we actually moved the vehicle physically over and seen it. But of course, we never do that. It's not like we fly around and perturb it. We just get one flight, and then we actually have to figure out from what we measured, what is it we think we would have measured. Now, the reason why there's two tubes here is you can imagine that because of the extra uncertainty, you have to increase the size of the tube, right? One tube is accounting for uncertainty from a process noise perspective. The other is accounting for uncertainty from a sensing noise perspective, and you have to increase the size of the tube as a result, okay? So what we use the nerf for, what nerf is basically, we tried this with meshes. You basically take the camera images, you make a mesh of the world, and then you essentially use the mesh world and you sample from it in these perturbation states. That's one way of doing it. Turns out to fail miserably. Nerfs are just another way of representing the world. So basically it's a way of capturing the image stream, and you essentially create the 3D version of what that image stream looks like. It's stored in a database in such a way it's very easy to sample. So when we do the perturbations, you can actually sample from that nerf representation of the world, and that's actually what the tube nerf does. Everything else about the tube nerf is the same as what I described. It's the nonlinear version with the nerf used then as the mechanism for actually extracting information from it, okay? So this is the, so now we implement this. So what we're now doing, the difference is we're no longer using Vicon. Everything here is using onboard sensing. The sensing is looking down here. And what we've now learned is a policy that's figured out how to fly using that as the input stream for localization, right? Which is pretty grainy and miserable looking. And then furthermore, we stuck this thing on it, which is a hanging pendulum, which has two effects. One, it's influencing the dynamics in ways that this thing knows nothing about. That's not in the model. So we're handling that as an uncertainty on the planning side. Meanwhile, if you look closely, you would have seen the thing swings underneath the camera, and so it's messing up the image as well, and yet it's handling that from a vision perspective as well. And so now we're flying around. Again, you would expect errors that are going to occur, but they're not going to accumulate. But like I say, this is perhaps another image. You can see how the thing is swinging around underneath it, messing up the image. But again, same deal. We've hammered the thing with these leaf blowers and tolerate that type of robustness as well. But everything looks the same as what it was just now, but we're now using onboard vision instead of the Vicon, which is a big difference in terms of implementation robustness. Okay? All right. Now that's all fine and dandy, except for the fact that the world changes and or things fail. And one of the things you'd like to have is everything I just described, have it be adaptive to whatever it is that changes in the world. And that doesn't mean relearn the policy, okay? Because as described, that's a 20-second exercise. What you want to have is something that's onboard adaptive in the sense of it recognizes things as different, it does something about it. And so basically what we have then is in the learning process, we actually give it a data stream, which is an indicator of essentially what the input-output looks like, and what the policy learns at the same time as it's learning the policy. So it learns how to do this right, and at the same time what it learns is how to diagnose when things aren't looking that great by looking at this input-output stream. And then essentially, again, doesn't adapt the policy, but it has an extra input-output stream that it looks at, which you can then use to figure out how to actually change what is coming out of the policy. And that's sort of this notion of adaptation that happens here. So in training, this signal is given to it, and it learns how to diagnose from that signal whether or not things are looking good or not. And so we have failure cases that we train it over as well, and that basically it sees that signal and recognizes there are problems and figures out how to do things differently as a result. But basically what happens is, again, I mean, there's sort of training time spent and we're faster than that, but what I'll show you is what the result of this is in terms of what we can implement. It gets into a lot of details here about how it's implemented, but the net result is we can implement things faster, we can learn things faster, and the end results are really cool. Because we can now do everything I just described, but now we just take one of the motors and just fail it. And so now it's, right, so we're running the policy just like we did before, and if we ran the policy without any adaptation running, it would have just flown into the net and just died. But this recognizes that input-output stream says, hey, there's something different about this system than it was before, I need to do something differently, okay? Now, again, we've trained it on failure modes like this, so it knows that this is sort of a possibility. Keep in mind, it knows nothing about this pendulum. So if it looks like that pendulum's going crazy, again, you're trying to recover from a failure mode, you're gonna have some pretty crazy inputs. But the planner never knows about the slung mode, right? That's always an unknown to it. It's trained on failure modes with the motor. It never knows which motor is going to fail, right? It doesn't know that we're going to fail that motor. It just knows that a motor can fail, and if it fails, this is what it looks like, right? So now we have, so again, classic of an advisor. It's like, well, if you can do one thing and then you can do two things, then try three things. So now hammer it with the 7-meter-per-second wind. So you've got this howling gale blowing up this thing, plus you fail a motor while it's trying to handle a pendulum. And yet, while it looks crazy, it's not flying into the net, right? So it's sort of, maybe my bar of success is fairly low, but you have to keep in mind, if you've flown these things, you know how badly things can go, and they go badly very quickly, okay? So the fact that this thing is staying in the air, and while it looks crazy in terms of the motions that go in, this is actually stable response, is just trying to do something that's really, really hard, okay? There is no way of handling this type of suspension device any other way when you're actually getting hammered on by this wind that's so close to you like that, okay? All right, so and again, that's now running with all the adaptation on board as well, okay? All right, so enough about the sort of the planning part of it. What I'd also mention is that we are in this plane as well, where we're thinking about perception. And one of the things we've been looking at over the years is, again, from a multi-vehicle perspective, how do we collect information together with teams of robots? And again, we tend to do things for this work on the ground just because it's easier to deploy many things outside and do something interesting. If you know the MIT campus, you get a sense of what this is. This is the what would normally be described as the right-hand side of the campus. When you look at it, it's sort of over there with the main central part right here. But basically, what's also interesting about this campus is we have tunnels, so you can go above ground, sort of second floor, first floor, and underground. And so when you'll see paths that look like they're crossing, they're actually crossing in ways that aren't necessarily on the same level. Back up. I'm not sure if it changed so quickly. Okay, all right. So again, the motivation here is what we'll call cooperative SLAM. SLAM is simultaneous localization and mapping, but basically at the same time what we're thinking about is how to handle the situation where we are now able to work together to do this. So the type of situation you might be thinking about is vehicle 1 makes a map, vehicle 2 makes a map. You need to fuse these two things together. But there's an interesting question when you do fusion, because we often talk about fusion as a sensing estimation problem. Yes, it is. But you can't fuse things together unless you know that we're actually talking about the same thing. So I localized a building, you localized a building. Are these the same buildings? So this is a question that occurs before the actual fusion happens, which is, can you actually align things? And so there's an alignment step, and then fusion comes after this. And I would argue that fusion is quite easy. And you see a ton of people working on fusion, but it's the alignment question that's the hard one, which is at a semantic sort of binary level, we have to make an agreement that we're actually talking about the same object. So what happens here is actually at a frame level, and you actually see it here. There are two robots that flew through forest. They never met each other. They just happened to cross the same point of the forest, but not at the same time. But what they recognized was that the tree layout that they actually saw, the geometry of the trees was the fingerprint of the situation, and they recognized that that fingerprint was the same, and they were actually able to take the two individual maps, align them. What's cool about that is now you can start using someone else's information to execute your mission. So you can now plan your path in a map you've never actually created, but you've aligned it with your map, and now you have a fused map. And together, you can now work together to do a mission much more efficiently than you could before. So that's the sort of 30,000-foot goal of what we're trying to accomplish. The question is, how will this work? Well, again, you've got two issues. Communication, I mentioned at the beginning, comes up. We're actually doing alignment at sort of image level. And while I said you can't exchange video very well, it's actually quite expensive to exchange images as well. And so just taking 4K images and just throwing them out into the internet over wireless meshes is not a great strategy. If you have 8 robots doing that, you'll very rapidly just tie up the entire mesh network with these images flying around. And you don't know if any of these images are any good, right? It's just me recording stuff and sending it out. And that's super annoying. If you imagine your friend just sent you every image they ever saw, and you're like, thanks. Very quickly it shut that down and say, please stop sending me images because I have no idea if any of these things are interesting, and you don't seem to care. You're just sending me stuff. So you need to be very careful about the kinds of things that are going on here in terms of that scale. And of course, the other issue is going to be dealing with just the connectivity of the robots and how this information gets moved around. Okay? All right. So over the years, what we've created, and I won't have time to go through all the details here, but what we've created is this thing called Chimera Multi. So this is work with Luca Carloni and his group. He'd worked on Chimera, which is sort of a single vehicle, sort of VIO, which is onboard visual inertial odometry. Basically, it's a mechanism by which these vehicles now are actually using the onboard sensing capability to make these maps as they go along. But what we're trying to do is to implement this in a multi-vehicle sense and actually use the capability to synchronize the images and the maps between vehicles to actually create a one global map. But it may be distributedly known. Not every vehicle would necessarily have the same global map, but they're going to be iterating and trying to improve upon it. And so in fact, if you look carefully here, you'll see the image, the map solution converging over time as the optimization is running. And you'll often see that in these solutions, is it's not just an answer, there's a continuous implementation of an iterative solution that's been implemented. So built into that, this is actually, you'll see this here. You can see how incrementally this has been solved. And now these are robots that are driven around campus, and we're using each of the paths that they created. You'll note that some of these paths just don't align with things. They're not lined up with the building, so they clearly were wrong. They look locally right to that vehicle, but they're globally wrong, right? And they just don't know it's globally wrong until they are able to start fusing it with other information from other robots, and that's sort of why this thing continues to iterate, okay? So that was the first step, was how to implement this and get to sort of something close to fully distributed CSLAM. There's a bunch of code and data sets that are available online if you're interested in this type of work. And like I said, it was 8 robots driving around on campus. What's interesting about a campus, just like yours, of course, is it's a lot of interesting static things, but there's a ton of people walking around. You're above ground, below ground, different lighting conditions. So it brings a lot of dynamic complexity into the problem, and yet we're handling all that in the SLAM solution that we're implementing. So that was the beginning part, but we began to see 2 issues. One, the ability to do the fusion in this work, again, is requiring this alignment. So you have to have a situation where robots are actually driving not in the same direction, but possibly in opposite directions, would recognize these geometries and these parts of the world as being the same, which is quite complicated, right? Because you're down on the ground, you're not seeing a lot of interesting stuff. There's no sign that says you're here now. You're just driving along, you see a bunch of cars and a bunch of wheels and a bunch of windows, and it's like, okay, is this the same set of things that this other guy saw? If so, like, does that mean we're in the same place? They may not actually be in the same place. We're just looking at the same things, right? And so there was a question of how to do that, and one of the things we noticed was right here, there's 2 robots literally driving down the same sidewalk in opposite directions, and the result of the fact that the blue and the red are not on top of each other indicates that they did not recognize for that entire time they were on the sidewalk that they were on the same sidewalk, okay? So there was a fail of the techniques that we were implementing. And the other thing that was happening was just super slow convergence of these things. We were running the equivalent of distributed gradient optimization. And if you've done optimization, you know gradient things tend to be slow, so distributed gradient's even slower than that, and then the result is it just takes a long time for this thing to converge. So you do see these iterations, these things moving around in the solutions, but they're not moving very quickly. So what we wanted to figure out was how to speed up both of these things and make them better. So on the front end, what we were looking for was a way of trying to minimize the amount of information that had to be exchanged. So we're not sending images, and again, this is us flying over a forest. And I don't send you a picture of a bunch of trees that I see, because you can imagine how useless that would be, right? Here's just a bunch of trees, here's more trees, here's some other trees. what we actually try to figure out from that image is what is the geometry of the interesting things that we see. And it looks like this. Now, early on, the name for this project was Blob Slam, right? So we're doing localization and mapping based on blobs. And what are the blobs? Are these things. Where do they come from? The code can segment anything, which is very good at segmenting anything. What it can, you give it a bunch of trees, it segments trees, and come back and says where the trees are. No localization be done, nothing else. It just simply says there's a bunch of trees in the image. Okay? But we can then run a localization algorithm. You're basically doing frame-to-frame alignment from these things. From that, you can start localizing, which is what the dots are. You now know where the trees are located in some map sense. And the idea is that what I do is I give you I'm now extracting this image into a very sparse representation, which is effectively these blobs. And what I can now tell you is this is where blobs I think I've seen. I give you basically a bunch of blobs. And then you start comparing my blob stream with your blob stream, and we actually start doing the alignment. And the alignment ends up looking like this part of the picture over here. Vehicles flying, extracting sparse dots. Other vehicle flies, extract sparse dots. And you're basically doing the alignment, which is do these two geometries line up? Okay. But again, keep in mind, this is a long, like you're flying, you just fly through a forest, someone else flies through a forest, and now you got to figure out where all these blobs are. This is why you want sparsity. You want a sparse representation of a very complex big thing, which is the map you've seen of the entire flight. Because you're going to have to actually go back and try to line up the geometry over the entire geometry sequence that the other vehicle has seen to look for things that look like loop closure, which is the frame alignment step that happens here. And if you can do that loop closure, what you can now do is check the box and say, yeah, we were actually in the same place at different times with high confidence, and we can now say thumbs up. Our maps can align, and now there may be drift after this, but we can be confident, at least at that time instant, there was alignment, and now we're confused because we've aligned the maps, okay? So that's what basically the sequence is here, and so this is a way of getting into the front end and actually handling this situation of what was happening in Chimera Multi was we weren't getting good alignment. Now we can actually fix that and start getting good alignment. What it looks like is, what's interesting is just how well this works. This is a video sequence from Finland where they had summer, they had spring, they had fall, they had winter. And so you go from trees with shadow to dead trees, and yet you're still looking for the same basic geometry and able to do the situation where we can come up with geometrically consistent linkage between the frames and the blobs in the frames, even across different. So this is fall and this is summer, and now start thinking about the alignment between them. And again, we're extracting the blobs, able to figure out what these are from these large-scale features, and actually do the matching between them. So this is SOS Match, which is sort of the front-end alignment tool, how it works. Again, a lot of data here, but basically this is a data set with lots of different situations. We wanted to show this is robust across different lighting conditions, different sort of situations in terms of the actual things we were looking at themselves. So we're comparing different cases, pretending like there's just a UAV flying around the same path at different times of the year, and we're basically saying, hey, have you ever been here before? And it's coming back with fairly high levels of precision and recall. Our numbers here are not that much different than the other algorithms that you might think about using, or ransack and SIFT ransack are classic ways of solving this. What's very cool about ours is just how small our maps are, okay? So these other maps are in the 400 megabytes. Keep in mind, what this means is if you want to share a map and have someone else align their map with your map, I have to send you 400 megabytes worth of data, okay? Every time I want to do that. And again, if you've tried communication systems, sending somebody somewhat continuously 400 megabyte things, not going to work, okay? But if I can send you something as 0.05 megabytes, I can basically just free stream that and basically have you pick it up and use it whenever you want. So the key here was to keep the performance about the same level, significantly shrink the size of the map, and now we can do the localization or the frame alignment between the vehicles. And so this is essentially accomplished that goal, and again is robust to the different kinds of situations in terms of the weather, the spring conditions. Okay. I won't say too much more about the back end because I want to get to the PUMA work, but based on the back end, you have the classic difficulty is, the classic scenario is the centralized doesn't work because you got to send all the data to one place and then do a whole bunch of optimization there. So you end up with one guy just super heavily loaded, plus every one of these links is just super, carrying a huge load in terms of the, actually it has to be exchanged. So the flip side is what we've actually implemented, which is fully distributed, where everybody's like helping the calculations. So the calculation is very distributed. The communication load is somewhat cut down. But so this is fast-ish, but slow because of the fact that we are relying on this computational node. This is slow because of the number of iterations required. And of course, there's always that, well, what about the middle ground? The middle ground is hierarchic. What you try to get to is some type of implementation which is able to distribute the computation but have a central node that can speed things up. And that's actually what we've been implementing. And this is the last chapter of Yulin's PhD thesis. He did a lot of cool stuff. He ended up 7 journal papers out of his PhD alone. This was the last one, was looking at how to handle this hierarchical implementation. What's very cool about it is perhaps capture this by this image here. So essentially, if you're running gradient, you're up here. You're just very slow convergence. A typical gradient plot would have iterations counts up to 1,000. And you'd see a nice reduction in performance, right, or sort of the error, but normally you'd be like way over here on the graph, okay? If you ran Newton, right, which is the second order type method, which is the thing you'd normally try to do if you're running optimization, yes, you could, but any type of Newton optimization requires a good gobs of information go to one place so you can actually run a Newton. You can't run a distributed Newton, it has to be in one place. So you're back to the central calculation. Newton converges super fast, right? So great. If you could do it, get it all there, you can run Newton, fantastic. What Euler was able to find was a middle ground, which is this set of things here, way faster than we were getting before. And in 5 to 6 iterations, which is more than Newton requires, but within 5 or 6 iterations, we're now getting to error numbers that are very small. So fantastic improvement in the capability of what we could do before. Okay? All right, so a couple of last words then about PUMA, because now I'll say about Mater and our Mater on the way. So again, this is the Panther that I talked about. And this is the beginnings of our understanding of the value of the imitation learning. The classic, we had Panther running up here. It was actually what's implemented in this video. Performance was okay, but it was getting kind of slow. And the question was, how do we speed this thing up, right? But it occurred in 2 steps. One, we said, well, let's try to make it better. So we try to make it better by including more stuff in the optimization, and you went gold to green, right? So in making things better and including more stuff in the optimization, and keep in mind, this is a log axis, you're up to 10,000 milliseconds, or sorry, 1,000 milliseconds, which is normally called a second, right? And if you're optimizing and you're flying and your optimization computation takes a second, that's no good, right? This is not implementable. So this is where we wanted to go gold to green because we wanted the implementation to get better and smarter and be a better designing algorithm, but we were stuck up here. And the question is, how do we get down here? And this was the imitational learning. It's actually the very first implementation of imitation learning that we did in my lab. And this helped us to start understanding, now we're in the tens of milliseconds, we can now actually get into a situation where this is going to be implementable. And that got us to what we call Deep Panther, getting into the perception aware. And that's actually what is running on board here in terms of the actual code itself. And so that was the beginning of understanding it, but that's one vehicle. And there were other vehicles flying around, but they were just obstacles. What we wanted was a distributed implementation where you have multiple of these planners running. And so not just one thing running, but now running many of these things. And the question is, how does one handle this situation where each of these objects in here, all of these things moving around are planners, and they're all planning in a world where you don't have one centralized calculation running. Each one of them is running asynchronously and in decentralized fashion. And what you then have is a situation where you have to deconflict. Like if I decide to do something, I have to tell the world this is what I'm going to do. You hear about it, you plan around what I'm doing, and you basically take what I'm doing as a given, which begs the question, how quickly did you learn about what I was doing? Because if there's communication delays, there may be a situation where the information I'm doing this arrived later than I would have hoped, and you then have to handle that delay. And the question was, how do we handle that? And that's what our Mater did, and basically enabled us to have a situation where we could fly around and asynchronously sort of deconflict while avoiding the other vehicles. A lot of details in the paper here for both Jesus and Coda on how to handle this, but let me show you what it looks like in real life. So this is running our Mater on board in our lab, and we're flying around with some obstacles, but a bunch of planning agents. So I think in this case there's 4 planning agents and a bunch of other obstacles that are just in the way. So we have to figure out what they're doing and fly around them, but we also have to deconflict from every other vehicle that's also planning in the world. And this gives you an onboard shot, and you get a sense of sort of what it's like to be in this world. Kind of hard to see things at times, so this is why the perception aware is necessary, to be able to look at things and pay attention to them. But all this is implemented over a mesh network. So you take those vehicles that are they're using Vicon for knowledge, but on the other hand, like for their own knowledge, on the other hand, all communication between the vehicles is done over an onboard mesh network, and that's how the communication happens. So if I'm planning something, I communicate it to you over that network. So then you got to be cognizant of the types of delays that one might see and actually anticipate what the effect of that would be, which is what our Mater does. Okay? So that's the vision for the multi-agent version of sort of what I've shown. So if you think about the very beginning, I'm talking about a lot of details about single vehicle stuff. This is how you then embed that maybe in a multi-vehicle framework. But along the way, you have another issue that shows up, which is everything I just described is me planning a path in what I will describe as my frame. Right? Although I'm getting Vicon data, I don't necessarily know what frame I'm in. And certainly in a situation where, like if I start running the VIO that I described before, I'll be doing localization using the hieroglyphics I'm looking at. But you get what's called frame drift, right? I create errors every time I solve this problem, and these errors tend to accumulate over time. I never actually know where I am. And I get drift. I may know at the beginning, but I get drift of that frame as it goes along. So any decision I'm sending you is in my frame, like that's the only frame I know. And you make decisions in your frame, but your frame is drifting as well. And so you then have to go back to what I talked about with the frame alignment problem, that on the planning side, I can't trust any information you're giving me unless we can align frames. This isn't a perception problem, this is now a planning problem, but it's a planning problem that's coupled tightly into the perception part of the problem as well. If we can't align frames, we can't exchange information. If we can't exchange information efficiently, then we can't do the collision avoidance efficiently. So then we have to start running PUMA, which is perception aware, uncertainty aware. The uncertainty aware part of it is the frame alignment. And so what's down here is essentially that same SOS match that I described to you. We run that as the first step. We have to align frames. If we can't align frames, then we can't do the sharing information efficiently or even effectively. But that alignment never is perfect, right? There's always errors. And so what you have to account for is the error in the alignment, which then couples into the error in my knowledge of what you're doing. You said this, but there's error in what you're going to do anyway. Now there's error in the alignment. And so in my planning, I now have to start thinking about how much error do I start putting around essentially your path. And of course, now you get to start thinking about the tube concept, right? Where it's now me planning a collision avoidance around a path, if it's me planning collision avoidance around a tube, where the tube now size is actually a function of both how confident I am in what you told me and how confident am I that I've actually done the alignment. Okay? And that's what PUMA is doing. And so it's trying to balance exploitation, which would be you give me information, but maybe I don't believe it. And basically what I would then do is you give it to me, but I then have to be aware of the fact that there's errors in it, and I then have to explore. And so what I do in my exploration is I use my ability to sense to say, well, look, these are things that are important to me. You're close to me, but I'm not very confident in what you're doing, but I can look at you, and now I can use my onboard perception to reduce the uncertainty in what it is that you told me, and I avoid all the other alignment problems, but of course I only have one camera, right? So I have to figure out what I'm going to look at and then track it. So this becomes part of my planning problem, which is to figure out what to look at based on the uncertainty. And what's cool about this is the uncertainty is directly embedded into the mission, right? And so if there's a lot of uncertainty and I have to fly around something, that's recognized as poor performance. And so uncertainty reduction is built into the mechanism, not as a statement of reduce uncertainty. What it does is try to maximize performance. And it says, look, this uncertainty is creating bad performance, so let me reduce the uncertainty because that will improve performance. And that's what's really cool about the algorithm as it's implemented. So again, PUMA is what we run. This is what it looks like in our lab. All these dots are lining up, which is what's supposed to happen. And so you get a sense of this is a baby version of what I showed you for the UAVs outside. But this is the kind of thing it will look like in our lab. And this is what PUMA looks like. Let me see if it actually runs. Like I said, it's PUMA Lite. We're not there yet, but basically what we have is there's an obstacle. These vehicles with their visibility cones are looking at this thing as they fly around, but they're making decisions about what to look at based on what's creating the most uncertainty, what's having the biggest impact. And of course, all of this is a planner that becomes our expert, but we're doing invitational learning of this and then implementing this online. So everything else I talked about as the mechanism to get this to be implementable is built into the backbone of this. Is just that what we're now solving is a much, much more complicated optimization problem, because this is multi-UAV, perception-aware planning, handling all the uncertainty, thinking about where to look. All of that is built into this optimization framework in the learning part from the expert itself. And so that's what's going to be, like I say, is implemented, and we're going to be running that probably for the ICRO videos that we make in the next month or so. Okay? All right, covered a lot of ground, talking about the entire autonomy stack and the pieces we're looking at, but we've got SLAM, perception aware, a lot of planning going on, a lot of work of lots of different students, Coda in particular, Andrea, and then Annika as well in the more recent work. Like I said, there's a web page with some papers. It's never up to date, but you know, send me an email if you can't find something you'd like to take a look at. With that, I'd like to thank you for your time and look forward to any questions you might have.
Okay, we have time for one question. In the meantime, if the speaker and Paul can start to set up the panel for the next session. Any question?
Hi, John. You talk about perception and uncertainty awareness. So how did you quantify the uncertainty? And then you are planning how to embed this kind of uncertainty and optimization or searching?
Right. So great question. I mean, of course, there's many types of uncertainty. So in frame alignment, you might look at things at how confident were you in the actual frame alignment. So the frame alignment algorithm actually spits out the equivalent of a covariance matrix. So it's giving you the translations or rotations plus the covariance of it, gives you a sense of how bad you think or how badly you think that happened. So that's sort of one piece of it. But normally it's going to be an element of like we have this question, this problem whenever you're doing path planning is where do you, like you're doing future propagation on about the same length scale as your path. So you have to think about, say for the flying lampshades, we are tracking them and then we get a position velocity stream and then we just do a propagation forward using a very simple, like effectively one R squared dynamics. So we don't do a very sophisticated model. So about that, we just put a huge cone of uncertainty that just grows, and we just add the sort of process noise type of uncertainty we would normally add to something like that. So again, you could get more sophisticated in that tracking algorithm, but there's just so many things in that uncertainty we just don't know, and it all piles up. And you can quickly end up with a robot that just doesn't want to do anything because the world's just full of uncertainty, and there's big uncertainty bubbles everywhere. So we try to be careful and minimize the amount that we put in, but be smart about where we add it as sort of the key pieces. And like I said, the alignment to handle the fact that with the any planning that's done in different frames, when we translate it to an R frame, we have to account for that uncertainty. Is one of the main pieces we've added recently. Okay. Okay.
Thank you very much.
Great. Okay.
Thank you for your.
Do you need these as sorted microphones?